Okay, welcome back. Last video was all sorts of signals and things like that, and we got as far as this one. Uh, this one had a fairly nice background. We got to see this hydrogen snake show up, and it's got some bright spots in yellow. That's interesting. It's got this curvy shape to it, sinusoidal shape. That's pretty interesting. Um, Exciting. Now, what else can we do with this? If we take each vertical line sample and figure out the average value, over here, the average value would be a certain number for this vertical line sample. Now, this vertical line sample would be a little bit brighter because it's got some yellows to add to the average. Here in the middle, it would be kind of a low number again. And then we might get a bigger number over here in a vertical line. If we looked the same way on that original yellow graph where we saw a ghostly image, for the antenna, we would see something like this. Here's some bumpy stuff going along, then it goes down, it goes up, it goes down, it goes up, and it goes down. So this is the average value of each sample walking through all the samples. We saw something like this with in the spreadsheet calculations. We saw some grass bumping along here in the middle, and it went down and up and down and up. And one of the samples had a whole bunch of hydrogen, and that's what's showing up here, increasing the average value. If we look at the reference of all those resistor values we had at one point, it looks the same pattern as the blue line just before this in all sorts of ways. Maybe this bump isn't quite as high as the blue line just before and goes down and back up. We can compare ant to reference. The next signal we played along with was ant B. That's where we actually started seeing some yellow spots going on the page instead of a faint ghost. Here, the average value goes along low, goes up high, down, kind of bounces along low, goes up even higher over here in this range of samples in time, and then goes down low. The next one we calculated had something to do with references, ant RB, not A, that would be the first letter of the alphabet. B was the second calculation. It goes down even kind of lower and flatter, goes up, low and flat, and then up and down. That's a pretty nice signal. The next signal is some more calculations going on. We'll talk about what this thing is, ant X. And then this one is actually TVT for trimmed, and then something to do with velocity, and then trimming again. Goes along low, up, goes back down low, and then up again. In each case, that second bump was higher than the first over here on the left. If we take all those calculations and put them here on one page, it ends up like this. First, I'm going to draw attention to the very bottom one. This is the galactic latitude in degrees. Sometimes the antenna was pointing down below the plane of the galaxy. The Earth rotated, and then suddenly the antenna was looking right into the plane of the galaxy at 0 degrees latitude in galactic latitude. And then sometimes the antenna went above the galactic plane and then came back down to the galactic plane and then went down below again. It went from below to above to below in one day. That makes sense. 2 times it crossed the galactic plane. That's kind of where we expect all that hydrogen to be in that flat pizza pie of the galactic plane. And we crossed it in two places, galactic crossings, I call it. Over here on the right, we can see it most clearly. The signals kind of had bumps. Way up here in the antenna, I hardly see anything going on. In the ANT B signal, sure enough, there was a bump at the right place. The reference didn't know anything about it. That makes sense. Here, ANT RB, this orange signal, had a bump in the right place. And this next one down here in the middle, ANT XTVT, did some calculations and has a bump in the right place. And that's true over here for this vertical line here. We see bumps probably in the right places. Not as big, just like we saw in the earlier graphs. This is a different kind of graph entirely. This one has to do with time. For every sample from 0 way up here to sample 907, we know that the sample recorded a timestamp. It includes the day and the time. In this case, we're just looking at the time mostly. It went from a value of 0, because the file started at the beginning of a start of a UTC day, and it went almost up to 24 hours, 23:58, where it ended the file. So it went from the beginning to the end of a day in time. On the Y scale is fractional days starting with the first day. Well, we said we started essentially at the beginning of a day. So sure enough, it starts at 0, this green line, which goes all the way up here to this top value before it stops, right at the end of one day. Just like it says down here, just about 24 hours. This is fractional days. And if it doesn't show a straight line, then maybe you should try to figure out why. I do see one small imperfection if your display will show it. Let's look at the next plot that explains why. For all those raw samples, meaning antenna and reference samples, what is the spacing between them in time? How long has it been since the last sample? I look at this number, which is the median value, to say that this line, all these dots, are about 47 seconds between since the last sample. Okay. I'm glad they're all about the same. It's interesting that there are some outliers. These two samples are bigger than 47 seconds. And over here, we got 1, 2, 3, 4, maybe 5 samples that are greater than 47 seconds. That's when the operating system simply took the computer away from us, didn't give us any CPU cycles to collect data, and so it took longer. The operating system might be talking to the hard drive and reorganizing something. It might be talking to the internet. It may be taking lunch. I don't know. But the computer went away for a while, and so it took longer for us to collect some samples than others. ezRA has a plot for everything, so the next plot is simply different stuff, but of the same character. This is the spacing between ANT samples. We were collecting ANT reference, antenna, and then a reference, antenna, then a reference, alternating every other one. So the antenna one should be about twice as long. The median value down here in blue is about 95, and that's about twice what we saw before at 47. That makes sense. There was a reference value taking up time in between those things as well. In the same way, the spacing between reference samples is shown on this graph, and it's got the same kind of information. Interesting that there was only one sample spacing that was longer. Okay, interesting. All right, so we ran EasyCon. We were looking at a whole bunch of EasyCon plot files. There were a lot of signal files we went through in the last video, and even more in this video. We even looked at some time information plot files. But it says here that EZCon, CON for condense, spits out a file called EZB. Everything has to be named easy, so .ez. And I didn't want to use the letter A, so I used the letter B, the second letter of the alphabet. So EZB are condensed data files. They look like a lot of numbers. Holy cow. Lots of columns of numbers. These files are physically smaller than the previous data file. This is supposed to be condensed. This is the result after all the math was worked on it, after we started calculating those different signals to try to improve the image of our hydrogen data. It turns out that there are a bunch of titles along the top here. We'll go through all of those. And underneath it, there's even a row of numbers that kind of line up with the titles. They won't necessarily line up with the columns of data down below because I don't know how many characters are in each column. Let's zoom in here, this top left, and take a closer look. Here's the top of that file. It starts out with a comment. It says, who created this file? This one came from a program called ezCon, and then it has a revision. In 2023, the last two digits are 23. 02 means February. 09 is the 9th day. A was the first revision, and it was a Python program, .py. The command that created this file is also recorded as a comment. Somewhere up in the front, you'd put Python or maybe py in Windows, and it had the rest of the line was this thing here. It had the name of the program, ezCon. It had a data file, and that was it. But ezCon has all kinds of knobs and switches you can adjust at the command line level, and it would be recorded on this big long line for posterity. You might have gone to a lot of trouble to get the right values in that command line argument list. And at least .ezb file will record what you did to get there, so you can get there again. There's a blank line for line number 4, and then it starts talking about the telescope, where it is on Earth. Here's the latitude, then there comes the longitude, the altitude above mean sea level in meters, and then the name of the telescope. This was N0RQV, that's my ham radio call sign, and it's an 8-foot dish in my backyard, so I got -8. What was the lowest frequency bin out of all those frequencies? It was 1419.2 megahertz. Here's the maximum frequency that was used. How many frequency bins were there? 256. And then comes a whole long list. It even falls off the page here. This is the menu of columns in this EZB file. The 0th column, 0 column, is something to do with time. Here's the first column. So now we can walk through them all. But there is a clue about what all these columns are inside the file. And then comes all these columns. You can see them neatly laid out below. Each sample has one line of 20 columns of information. I guess every one of them is a number. Not really any characters in there, except maybe an E for exponential notation. All right, what are these different columns? It turns out that the first 0 through 9 columns are unrelated to the radio information of the sample. The very first column, column 0, is the time in UTC time in modified Julian days. Now, a Julian day is the number of days since November 17th, 1858. Holy cow. Um, it's a standard. It comes up with a nice, convenient number. It's not numbers since 4000 BC, which is a Julian date, is measured after. So modified Julian day is a smaller number and takes up less space on a hard disk. And it's a fractional day. You might have 0.5 for halfway through that day. You might have 0.25, whatever it is, a fractional day, a number, period, and some fraction. The next column is right ascension in hours, and the next one is declination in degrees. This is the way you would find a star on a star map. That's the coordinates for the sky above us. Another way to look at it is, how does it compare to the galaxy? What is the galactic latitude, meaning above or below the pizza pie of the galaxy? Or are you looking to the left or the right of the center of the, when looking at the center of the galaxy? That's what the longitude is, left and right across this pizza pie. The next column is VLSR, which stands for the velocity from the local standard of rest. Holy cow, what is this all about? We'll talk about it later, but it has to do with the Earth traveling around the sun once a year, as well as the Earth rotating on its axis once a day, once every 24 hours. That affects whether that stuff in the galaxy out there is coming towards us or going away from us. VLSR is defined as things going away from the base of the telescope. Is it traveling away from us at some kilometers per second, or is it coming towards us? It's a bunch of math having to do with where you're pointing in the sky, what time it is, and where you are on Earth. Hooray for computers. The next column is count. This was an idea of mine to maybe I was going to combine ezB files, and this would allow me to take averages of all that data. How many ezB files am I combining? The next two columns were spares, but now I'm redefining them experimentally as azimuth in degrees and elevation. That's kind of where we're pointing that military cannon. Where are we pointing the telescope with respect to the ground around us? Are we pointing north or south, or how many degrees up from the horizon? There are more columns, though. The other columns are all this information we've seen before. The antenna, that's the average for each sample. What is its value? What is the maximum value in each one of those samples for the antenna? Same thing, but for ant B, an average and a maximum. Here's the reference, average and maximum for each vertical sample. Ant RB was another calculated signal. Ant XTVT, I've talked about a little bit. It gets columns for average and max. And we've already just talked about the galactic latitude in degrees is in there already. Here's all those columns again. There are 2 of them for antenna, 2 of them for reference, 2 of them for ant B, 2 of them for ant RB, and 2 of them for ant XTVT. We did all these calculations. It's time to save them into a file. Not just all that coordinate stuff, but the signal stuff as well. You get 1 value per sample, so we're condensing the data, but you get an average and a maximum to study. I said there were 20 columns. There's one more. Number 9 is kind of left over. It's strange. It is ant X TVT. That's the signal just above here. But it's the center of mass of its information expressed in Doppler. What are you talking about? Well, when we get spectrums of galaxy crossings where the action is, we see a lot of hydrogen information. In fact, sometimes we see not just one peak, but we see another peak. Sometimes it's over here on the right in positive Doppler uh, locations with a higher than the center frequency. And sometimes it's over here on the lower side, lower than the center frequency. We talk about the center of mass, we start talking about that this information about hydrogen is farther from the zero than this information. But this is a whole bunch, and this is some. We should take that all into a center of mass calculation and kind of get one number to say, kind of where is this blob of information? Is there a whole lot of it to the right or a whole lot of it to the left? And by how much? Give it to me in megahertz and tell me kind of where the center of mass of this thing is. I thought it'd be an interesting calculation. I think currently the program actually writes zeros because I need to go back in and put in the code that I disabled somehow before. But that's what that column will be. All right, we've talked about the ezB file and what it does. Let's go use it. Here's a program called ezplot. Of course, it has to start with ez, and it writes plot files too. We talked how there are 20 columns, at least 10 of them are signals, so ezplot has a whole bunch of things it could chew on. Let's look at a couple. If we look at ant B, that was that green signal we had before, but we take 5 ezB files now. Now they're smaller after all that math occurred. We can plot this out real quickly. Here's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 spikes, 2 per day. So that's 5 days of information. You can see that it kind of repeats. There's a big tall spike every other one, but still there's a bunch of variance going on. It's got the general same shape for over 5 days. We're up to about 4,000 samples now. Okay, here's the next signal over 5 days. Ant RB. It also has 10 spikes. Now we can see a little more clearly that all the tall spikes are about the same place instead of jumping up and down. So that's a little smoother. The next one is that mysterious Ant X TVT that I've talked about. And it has 10 spikes. It's even a little smoother as it goes across. Its color is kind of this purple violet color. If you take all of those things going on, the blue is the ant. There are 2 of them, average and max. Reference gets 2, average and max. Ant B has an average and a max. Wow, the max has all kinds of noise on it. Ant RB goes along. It has 2. It has 2 for this violet one. And down in the bottom is our friend, the galactic latitude in degrees, above and below the galactic center. And what we find is for the samples that are when the antenna is pointing at the galactic plane, crossing the center here, crossing 0 degrees galactic latitude, we get a spike. We get a spike on all those galaxy crossings, kind of as we expected. That's where all the hydrogen is in the pizza pie plane of the galaxy. And every time we're looking at it, we see hydrogen. Things are looking up. All right, so now if we take those different signals, this one is Ant X TVT just for fun, and plot them by the same hours every day in UTC, they line up. That's good. 24 hours later, the signal shows up. almost. We look closely, we see that the brown is in the back. The brown was the first day. The next day was in red. The next is in orange. Then comes yellow, and then comes green. Some of you may recognize that as the resistor color code that electronic components were colored so we could have numbers on them back in the days before surface mount. Brown, red, orange, yellow, green are the first numbers, 1 through 5. The brown is like always on the right, and the green is always on the left here. What we're finding is for each day, this bump is moving a little bit to the left. It's moving a little bit earlier in the day. This is all related to the Earth traveling around the sun once every 365 days or so. But the Earth rotates each one of those, but not quite to the same star in the same place. It's 1/365th less than a full day. It's not 24 hours, about 4 minutes less. That's why this plot is shifting to the left. So let's plot it versus sidereal day. Then they turned out to line up quite well. All the spikes show up in the same place. When we measure it over 23.93 hours, a little bit less than 24. All right, astronomy is working. We can also plot it in the way that you plot stars on the sky in right ascension and declination. We'll get to that with the Easy Sky program. But if we plot it just in right ascension, here's the signal in right ascension, and they line up as nice spikes. What's interesting about right ascension is if you look up at the sky, it starts with a low number on the right and moves to the left as it increases. 0 on the right and increasing to the left is the way right ascension is pictured on the sky. That's why the big spike over here is now on the other side of the plot, on the left, pardon me. Holy cow, that was a whole bunch of plots to go through. It may not surprise you that I got lots more. Let's talk about them in a future video. See you then.